All right, I think I am online now. Good afternoon, everybody. Welcome to our first 2022 seminar from our EC seminar series. Well, we probably all were hoping by now we would have them in the real seminar room, but here we are. We're still online. Maybe by the summer. Okay, so for those who don't know me, my name is Zbigniew Wasilewski. I am a professor and associate chair for research at the Department of Electrical and Computer Engineering here at the University of Waterloo, and I'm really pleased to have with us today Omar Ramahi. Omar is a professor at the Department of Electrical and Computer Engineering here. He received his bachelor's degree in mathematics and electrical and computer engineering from Oregon State University. He received his both master's and PhD degrees from University of Illinois at Urbana-Champaign. Well, he worked from 1993 to 2000 at Digital Equipment Corporation, presently HP. He then at 2000 joined the James Clark School of Engineering at the University of Maryland at College Park as an assistant professor and later as a tenured associate professor. Moved then to University of Waterloo. Actually, I'm kind of looking real time, Omar, here on your resume, and I don't see the year you moved in here. When did you start at?
It's a top secret. It's big. I'm sorry.
Okay.
2005.
2005. Yeah. Well, definitely much earlier than I joined. Professor Ramahi's interests are in electromagnetics. Obviously, this is what he will be talking to us today. Renewable energy, biomedical applications, electromagnetic waves and fields, and so on. And he has quite a lot of accolades here, including fellow of IEEE since 2003, a book on electromagnetic modeling, computational modeling, 450 publications, and the list goes on. I invite you to read his full biography on our websites. Okay, so Omar, thank you for taking the time to speak to us today. And maybe before I hand the floor to you, just one technical comment to the audience. There will be question and answer period, of course, after the seminar. And the way we handle it, you type your questions into the Q&A function, not the chat one, and then Andrea will be reading them out, and we will have this kind of discussion going on. So, Omar, the floor is yours. Thank you.
Thank you so much, Zbig. Is you hear me well?
Yes.
Excellent. Thank you again, Zbig. Thank you very much for inviting me, for organizing, and also I want to thank Andrea also for doing the work behind the scene for making these seminars successful. So I was told I have 45 minutes. So I'm going to time myself carefully because I would like to hear from the audience if they have questions. Now, this is a bit provocative. Electromagnetic Lego. I mean, I challenge anyone to look at any book on electromagnetics to find anything related to electromagnetic Lego. So I'm not here to present to you how to design things, how to do things. I'm trying to present new ideas, okay, in the hope that our students will challenge what we teach them. This is the idea. For professors, maybe it's too late It's too late to challenge them, but for the students, it's not too late. All right, so electromagnetic Lego. Let me see here. I want to make sure that I know how to. Okay, so electromagnetic Lego. I think many of us have grown up with this idea, this game concept. It's a toy, I should say, not a game, but a toy concept that I think was invented by a Danish person. And the idea is that you have building blocks, and with these building blocks, you can make so many things. So this is the inspiration for, I would say, retrospective inspiration for something that we've been working on. What I mean by retrospective inspiration is that we worked on something for years and then we said, wait a minute, this can be perceived as a building block. So I'm being honest to you in terms of how our thoughts evolved, the evolution of our thinking. All right, so I would like to, of course, I'm taking the credit for this presentation, but there's so many wonderful, brilliant graduate students. There's so many to mention here, but they're never important to forget. So thanks to all of them, and most of them are graduate students from between Maryland and the University of Waterloo. All right, so what do we have here? What in the world is this? I mean, we're looking at a very complex looking tree, right? What does this have to do with the electrical engineering? Well, the idea, the reason behind me putting this is that I will not be able to understand this complexity in front of me if I did not carry an analysis. Okay, I have to analyze what's going on. I have to be a botanist, of course. But botanists look at this photo and they are not puzzled. They can explain what they see. They can probably tell from the leaves what kind of tree it is, how long it will live, the strength of the branches, and so forth. But the reason I'm putting it is that only through analysis, this is the point that I want to stress, is that only through analysis can we understand complexity. This is not, I would not say this is a scientific statement. It's more of a philosophical statement. But for us, in those fields in electrical engineering that are, I would say, hard to touch, hard to feel, mostly imaginative work goes on, we really need to develop a philosophical foundation. So I said that here I said only through analysis can we understand complexity. And I would complement this by saying only through synthesis can we, one, make things, and two, advance our knowledge. And the one and two can be interchangeable. But the bottom line is that synthesis is the way to move forward. We have to synthesize. And we cannot synthesize if we do not analyze. So analysis always precedes synthesis. And for the graduate students who are attending this webinar, this seminar, is that most of the tasks that master's students do is analysis, most of the time. And most of the time, what PhD students do is synthesis. You see, so you see the sequence of these two processes, okay? Now, what does this have to do with electrical engineering? What does it have to do with electromagnetics? You'll see in a second. Okay, so now I want you to reflect, especially for those students in electromagnetics, on the evolution of electromagnetics, sciences, and engineering. Why do we need to reflect on it? Because these are not constant fields. They change. They change based on many modalities, based on needs, based on our advances in other sciences, based on actually advances sometimes in instrumentation, based on advances in computers. All right, so that's not hard to convince anyone of. So if we look at the evolution of the theory of electromagnetics, and I would say that the theory evolved from minus infinity to early 20th century. This is, this is my estimate. When minus infinity, anyways, is a vague concept. You can say that minus infinity equals the Greeks, when the Greeks lived, or maybe before that. Anyways, but I can say summarize or quantify that period as such. Then we have evolution of solution techniques. Many people who work in electromagnetics actually, I hope this is not a surprise, but a good number, not many, but a good number, are good in solution techniques, but they're not good in electromagnetic theory, and the two are separate. The solution techniques, there was a reason, we don't have the time to go over it, why they evolved from the 1920s to 1980s, but in summary, it had to do with wars. Wars, World War I, World War II are the ones that gave the biggest jump in the electromagnetic science, and especially the advancement in solution techniques. And then we have evolution of numerical methods. I would say 1960s till now. All right. So the point is that we have evolution of everything that we're dealing with in the field of electromagnetics. That's a concept that I want to emphasize in this slide. So a theory, now people talk about electromagnetic theory, okay? Electromagnetics theory as far as the physics is concerned, i.e. Faraday's work. I'd rather call it Faraday's observation rather than Faraday's law, Ampere's contributions, Ørsted, and so forth. So that is the evolution of the science of electromagnetics. And that's different from a theory of knowledge for electromagnetics. And the theory of knowledge, and here I'm trying to point out to something that will help us come up with good designs, good things that will radiate or absorb or behave the way we want. All right. So let me make things more concrete, and let's talk about, for instance, the concept of evolution or design. Have things evolved or have things been designed from scratch? And here's an example, the dipole antenna. Almost everybody knows what a dipole antenna. It's a very simple. You just take two wires, open them, let's say a transmission line, you open it at the end and you create two flanging sides. The question that I like to pose is that we design a dipole antenna to meet certain criteria. Everybody knows that, radiation, pattern, impedance, efficiency, and so forth. But we have to realize that we start with a dipole. But the question is, why do we start with a dipole? Just because someone started with a dipole a long time ago? Maybe that person just had a dream, a revelation that the dipole is the right thing. But I don't think we can move on successfully and meet the challenges in life with that kind of thinking. Let's take a look at the microstrip patch antenna. And I'll show you photos of these in a second, but I want to emphasize a few points here. Still, many engineers don't like to know how and why it radiates. The microstrip patch antenna is the most ubiquitous, most available, cheapest. It costs a fraction of a dollar to make. And but not many people like to know why it works, how it radiates. Where did it come from and why? These are important questions. This is not, we're not talking about religious studies here. We're talking about engineering. And you will know in a second why these questions are important. Another example is transmission lines, and I will not go into that. So towards a theory of knowledge for electromagnetics. Okay, big statement, isn't it? Right? Towards a theory of knowledge for electromagnetics. Well, to put it simply, to understand how things are or how things work, we need to classify, classification meaning dividing, divide and conquer, okay? We need to classify, divide the things that we want to understand into least comprehensible subcomponents, okay? I like to be shown that this is not the case, how we, we understand things. Maybe in the QA, someone may pose a counterexample. To design to achieve maximum objectives, we need to synthesize and look at the parallels between what I said earlier. We need to synthesize using the smallest available subcomponents. Again, to design to achieve maximum objectives, we need to synthesize, but what do we synthesize with? With subcomponents, smallest available subcomponents. So the question is the dipole antenna a subcomponent? Obviously not. Is the microstrip patch antenna a subcomponent? Obviously not. Okay, so interaction, now comes the fun part. Interaction between subcomponents is the concept of coupling, okay? And the concept of coupling is pervasive, is everywhere, I think. We don't have the time to go into social examples, but even in social settings, coupling is extremely important. Meeting of the minds, we call it, the chemistry between people, all of this is coupling in the social setting. But in the mechanical setting, we have coupling between what you see here on the right-hand side. These are just sheets, metal sheets, right? And look what we can do with these metal sheets. We can build ships with these metal sheets. So the metal sheets are building blocks in this huge ship enterprise, manufacturing enterprise, okay? These sheets, they're standard, more or less, but look what we can do with them. Okay, now is there coupling between them? Of course there is. There is coupling between mechanical subcomponents, but it is extremely loose in the example that we have, and it can be strong in the coupling or the what we call the gravitational force between planets. Okay, so there is coupling, there is mechanical coupling, and many people try to here I pose the question, what does coupling mean? I'll talk about it in a second. So in the way we try to understand coupling between mechanical systems is through the pendula models. Very fascinating, and these models simplify the coupling. There's if you look from the left-hand side, you have two pendula. If there's no spring between them, they're not coupled. But you put the spring and you push the coupling to a new level. You may have a structure like the one you have in the middle, or you may have a structure like the one you have on the far right. Okay, so these are models. These are models to predict the coupling between them. But what happens at the end of the day is that the coupling dictates the performance of the system. This is the key point. Coupling dictates the performance of the system, or coupling dictates the form of the system. Coupling dictates the performance of the system, or coupling dictates the form of the system. The form of the system is something that I cannot talk about today. So coupling between electromagnetic system, the key is action at a distance. Action at a distance, okay? And that's the mystery about electromagnetics. That's the key mystery, is that things affect other things at a distance. And the distance can be near or far. And of course, this is relative. What do we mean by near or far? But it can be near or it can be far. And this is, in my opinion, the core of electromagnetic theory. And that's what astonished people, at the time of Faraday, is that, oh, look, I can do something here. I can affect someone, or I can affect something that is at a distance. And apparently there's nothing between the two. So, of course, for those who are in electrical engineering, they know what I'm talking about. I'm talking about Faraday and Ampere's observations. So coupling is everywhere: mechanical system, electrical systems, social systems, economic systems, and so forth. So here what I say is that mechanical subcomponents can be loosely coupled or strongly coupled. Similarly, electromagnetic subcomponents can be loosely coupled or strongly coupled. So, but we have to wait here. Is it the core of electromagnetic theory, the coupling between atoms or molecules, i.e. the electromagnetic properties concept? Exactly. So there's no surprise here, but we don't focus on this aspect. And you will see soon what happens if we focus on this, the outcomes of looking at this perspective. So before going any further, let us switch gears and talk about the evolution of antennas, and then I will go back into coupling. So the reason I want to talk about the evolution of antennas to motivate you why we're doing this work, okay? So this is not a philosophical talk. You know, we're not in the department of philosophy. We're Department of Electrical Engineering. We want to do things at the end of the day that are useful. So let's go and talk about the evolution of antennas. Okay, of course, one will say, have the antennas evolved? You will see in a second. So have antennas ever been developed from scratch? Again, I remember when I brought the example of that dipole antenna. No, the dipole antenna came from a transmission line concept. Very simple. You know, you have a wire, open it, and then all of a sudden it's radiating, all right? What about the microstrip patch antenna? Here's an example. This is a microstrip patch antenna. Professor Georges Deschamps, who's no longer with us, of course, living, he proposed this in the early 50s at a meeting in the suburbs of Urbana-Champaign in Arlington conference. And it's a very simple, it's a patch. It costs, again, maybe 20 cents, fraction of a dollar, but it radiates effectively. But why should I use it? Where did it come from? Just because he had a dream at night to use it? Actually, he didn't. He used the concept of cavities. In other words, his understanding, Professor Deschamps' understanding of the concept of cavities made him think about this patch antenna. But he did not use subcomponents, mind you. He did not use subcomponents at all. He used something that he thought of. What about optics and lenses? The dishes that you see on the right-hand side, they were inspired by the human eye or the animal's eye or the eye itself. What about antennas like what you see on the left-hand side, the Yagi-Uda antenna and its derivatives? Well, they were empirical. Still, we don't know why they radiate the way they do. We know how to design them. That's a different story. We know how to design them, but we don't know how they radiate. And so the question is, there's something missing. I hope you guys can feel, guys and gals, I hope you can feel that there's something missing. It's not that we're not doing something useful. We have been doing something useful, but are we reaching our limits? Do we really, can we push things to meet certain important challenges? We cannot if we want to continue relying on something that people dreamt of or people used and they found empirically to be working, okay? Of course, they serve a purpose, but that's not the end of it. Okay, so how do we characterize materials? How do we characterize materials? Well, as far as electromagnetic waves are concerned, either permittivity or permeability, right? And permittivity, loosely in the static sense, it's how the medium affects the electric field. Permeability, again, in the static sense, is how the medium affects the magnetic field. All right, so the concept of the building blocks. Let's go to the concept of the building blocks. Again, here's Lego on the left-hand side. Look what I can do with it. Can we do the same in electromagnetics? That's the idea. Can we have building blocks, not antennas that someone thought of and have them the foundation for our work? No, something that we can classify as a building block. Of course, here's some examples. This is a mud house. I used to live a long time ago in the capital of Saudi Arabia, and they used to have these mud houses. Now they took them down. But these are made of building blocks, actually. They are made of blocks. Each block has straws and mud, okay, just like that. And you can do many things. Modern buildings, same thing. All right, so let's look at the way the universe is created. Wow, that's a big statement, possibly. But it's things are made of atoms, right? Nobody denies that. Atoms have electrons, protons, and neutrons, okay? And the coupling between them is what makes things interesting, isn't it? I mean, what's the difference between copper and nitrogen? One has 29 building blocks, the other one has 7 building blocks. And the building blocks are identical as far as we know. But one is copper, the other one is nitrogen. One is solid, the other one is gas. So definitely you can see that the coupling is the key here. No, so let me just toss a philosophical statement. As humans advance in knowledge, they come closer to mimicking nature. Or if you want to look at it differently, mimicking God's way. All right. So the way we advance, we start mimicking, and our history proves that no matter how advanced we are, we go back and mimic what we find presently available in nature. All right. So here I say, keep in mind that building blocks plus coupling is the two things that need to be looked at, not just coupling, but the building blocks. All right. So if we look at electromagnetics, here comes the dawn of what is called metamaterials. Okay, I always like to question, or is it? So here comes John Pendry, who the Queen made a Sir in sometime ago, and he had a completely different perspective in the late 1990s. They're about 90s, from 1997 to 1999, where he came up with this concept of what later has become known as metamaterial. So what was so special about John Pendry? John Pendry said, let's mimic nature, okay? And I'll go back, and you see, John Pendry was a material physicist, solid state physics person. So he knew about atoms and materials in great depth. So he said, can we mimic can we mimic nature? Can we do something in the electromagnetic world that mimics nature? And that was really the dawn of metamaterials. I don't know if people have rephrased it the way I did, but I'm condensing his concept into the phrase that I just used. Okay, so basically, if you start looking at the what you see here on the left-hand side, Pendry said, if we put little things together, then we may create something that looks like artificial plasma. Okay, we may put, if you look on the right-hand side, if we put loops together, we may create something that resembles magnetic material. Of course, it will be artificial because it's not naturally occurring. It's not that you go to the mine and find that magnetic material. And of course, more exotic things later on. And so what happened is that putting these things together, you create an ensemble of small resonators, and there's a variety that you see here. There are 4 examples. Each one follows is workable in a certain frequency regime. This nice photo here on the upper left-hand side is in the, I believe, in the terahertz regime, and the one on the lower left-hand side is in the micro regime. But without worrying too much about these ensembles and what they represent, the idea is that you put little things together to create something, and that rhymes with our concept of using building blocks to create something useful. Now, here I want to take you, and especially the students in those who are listening, and look at how what happens when we have an E field that we shine an E field on a dielectric slab. So on the left-hand side, the E field is 0. So the dielectric slab, I did not represent it correctly. I put the molecules as if they were aligned here. But nevertheless, when you shine an E field on this material, you polarize this medium. So there's a process of polarization. Okay, polarization means you stretch the molecules, okay, or that compose that material. As such, this is a very simplistic, of course, perspective. But here you see that if we apply an E field, we stretch this material, we polarize it, we stretch, sorry, the molecules, we polarize it. And now what's interesting is that right now we have a field when we shine, one more time, sorry, look at this. When we shine an E field on this dielectric slab, what happens is that we have a new field, we call it E total, okay? We have a new field, we call it E total, and I think I should hurry up because I have 20 minutes left. We have E total, which is the incident field plus the scattered field. So what gives rise to the scattered field? Okay, now the question is, do we know how to solve this problem? Absolutely, it's a second year 370, 375 type problem in our curriculum. But do we understand the physics behind this problem? And I maintain that, unfortunately, we don't, okay? Not in a precise way. Simple problem, we know how to solve it. The way we solve it is that using boundary conditions. But the boundary condition is a mathematical construction. It's not a physical perspective. Okay, so back to metamaterials. It's an attempt to mimic nature, all right? See, I showed you the molecules. This is how nature, look what Pendry did. Pendry said, can we mimic nature? Well, he didn't use these words, but he said, can we put these little things together to create a new type of material? We call it artificial. And the idea is that if we take a molecular dipole here, like this, what you see on the left-hand side, that occurs in nature, I can mimic that using a tiny strip, a tiny metal strip. If I use a tiny metal strip, I will force the electrons to oscillate along the metal strip direction, okay? Very simple concept. I can use also, look at the electron orbital motion, okay, around the nucleus, and I can create something that mimics that, a little loop with a cut. We don't have time to go over why there should be a cut here, but we can manufacture or design a loop, a metallic loop, which forces the electrons to go in the circular direction, just hence creating a magnetic moment. All right, so, but can these little things radiate? See, one more time, I have a little metal strip, I have a little dipole. The question is, can they radiate? Here comes the fun part, in my opinion. Okay, the fun part is that, or the serious part, depending on how you look at it. If you're a professor, it's the fun part. If you're a student, it's the serious part. So here comes the fun part, is that when we put these together, things change all of a sudden. Wow, things change. If we put these loops next to each other, things change. We cannot use superposition. We cannot say the total radiation is the sum of each one, is the sum of the radiation to each one. If you do that, if you do the math, you'll end up with practically very, very little field. But in reality, when we put them together, we get excellent, interesting things, okay? So what is different now? What is different now is that the coupling between these molecules, that's what's different now. So if we look at this, these artificial media that you see we made on the right-hand side here, these dipoles, these little dipoles, an array of dipoles or an array of loops, what's interesting is the coupling between them. What does coupling mean? Coupling means impedance, right? All right, so just as in mechanical systems, different components are coupled mechanically to each other, multi-mode theory, etc., which I made a very brief representation of. In an electromagnetic system, all components are coupled, which affects the input impedance of each component. Here is the key, the input impedance, okay? It's the gate to radiation. So you've heard of this before, probably. The devil is in the detail. I think it's an American proverb or metaphor. Okay, I think that one can say God is in the details, but for us, the detail is in the impedance. That's the key word. The detail is in the impedance, but the impedance is just a name. It's just a name, a term we use to imply what? To imply capacitive coupling, inductive coupling, i.e. Faraday's and Ampere's observations, or the physics of Ampere's and Faraday's laws, all summarized in that impedance. Now, just to show you a quick example, here's dipole A, dipole B. Each one is separated from each other. Each one is radiating with joy, radiating a lot. You put the two together, all of a sudden the radiation is so little. Why? Because of the impedance. There is strong coupling between them. In this particular case that I show you here, on the assumption that the separation between these two is very little compared to the wavelength, the impedance is affected dramatically such that there is no power pumped into this system. You see, it's the impedance, okay? All right. Example, strongly coupled electromagnetic systems made of electrically small resonator. This is something that we did in our group. These are tiny little electrically small resonators. We put them together to create an ensemble, and look what happened. Okay, it turns out that this structure almost absorbs almost all the power. Look at the red curve that falls on it. This is the efficiency of this system or this plate or this surface to absorb energy. That's amazing. You have almost 100% efficiency. In this case, it's approximately 97. So all the energy that falls on this surface can be fully absorbed. And the reason is because we did impedance stitching, careful impedance design, such that all the energy falls on this surface, which is composed of an ensemble of electrically small resonators, i.e. building blocks. Isn't this amazing? I mean, I think this is really fascinating, is that we can have full absorption. There's no reflection back. All right. And the question is, can it be an efficient transmitter? I just demonstrated in this curve that it can be an efficient receiver. Can it be an efficient transmitter? But before we go into that, I just want to show you a plot of the power. So this is here in the bottom, you have the surface that I just showed you. And this shows the pointing vector. And you see that the power is funneled into these sinkholes. That's amazing. And now this is, if you contrast this to surface impedance concepts, it's impossible to arrive at what we're doing here using surface impedance concepts, for those who are familiar with surface impedance concept. But this is a very strong demonstration that all the energy that is falling onto the system is completely absorbed. All right. Because of time, I probably will skip this. But let me talk about metasurface as an antenna, okay? Can a metasurface, which is an ensemble of these building blocks, be an effective radiator? I just showed you that it can be an effective receiver. And the structure that I showed you is composed of these little building blocks. That's the most important thing to realize. So here I take you for a historical detour and look at the work of Huygens. I was told by the Dutch that it's pronounced Huygens, Huygens Principle. So Huygens was, in my opinion, he was, of course, very brilliant, but he was way ahead of his time, okay? So I say it's, meaning referring to the principle, and his to him. So, and he lived from 1629 to 1695. And many of us are familiar with Huygens principle, is that if you have a wave coming in and hitting a surface with small slits, then these slits act as a new radiation source for the space beyond the surface. And these two images summarize Huygens principle, okay? And the slits don't have to be separate. One can use a wide slit, and you can think that each point along the interface between the two media, the one on the left and the one on the right, acts as a source for the area beyond, for the right-hand side space. Okay. Very simple, I mean, think about it. Huygens did this before Faraday was alive, before Maxwell came into the scene, before Ørsted, before Hertz, before Ampere. It's amazing how he really envisioned that how this kind of model for radiation through slits or slots in perfectly conducting surfaces or opaque surfaces. And in fact, I'll tell you why I'm talking about Huygens in a second. Huygens formalism can even predict reflection and refraction. You don't need to use boundary condition. You don't need to use mathematics. You don't need to use variational principles. You can use point-wise, point-by-point Huygens formalism to predict reflection and refraction. That's amazing. And remember where he lived in the middle 1600s. So look what we're going to, inspired by Huygens' work and the building block concept, we say if we were to put electrically small radiators, each one of these red dots represent an electrically small radiator. Okay, if we put them next to each other with a separation that is much, much smaller than the wavelength, first of all, if there's no separation between, if the separation was quite large, each one would be an omnidirectional radiator, right? We all know this. Small, electrically small radiator. Almost. I know it's not physically possible, but almost. But if we put them close to each other, what happens is that the impedance between them start playing a huge role. Okay, now to make this more concrete, I'm going to put one of these radiators on top of a ground plane. And we know from image theory is that there will be no radiation below the ground plane, but all the radiation will be above. And the ground plane tends to more or less reflect the energy, bounce it back. So you see here, I have these arrows that are almost of the same size. Here, I use two arrows, different size, to indicate that when we have a ground plane, most of the energy is going in one direction, just, a representative schematic. All right, so I'm going to use this concept and put many radiators next to each other like this, and make sure that they're much smaller than the wavelength. And I can show you that these will become effective radiators. I effectively created an antenna. I created an antenna that is very flexible and is designed based on building blocks. Okay, based on building blocks. In this case, for instance, if I want to have an antenna that maximizes radiation in the normal direction, which you see here with the big arrow, I can have all of these sources phased equally, equiphase excitation. Okay, so what happens here is that the impedance coupling, the coupling or the impedance, i.e. the impedance is the same as coupling. Okay, as you remember when I said that coupling is what? Coupling is the capacitance and inductance between two elements. So the impedance acts as a power gate. It's like a floodgate to the power that is being fed to each of these sources. Isn't that interesting? Very, very interesting, I think. And so even though these are electrically small, collectively they can radiate very, very well. And I will show you in a second. So here, this is Huygens radiators. Here I can show you that I can phase the elements. I can phase the elements, and I can even control the direction of radiation. Is there any equation behind this? Not at all. It's very simple. Is the theory robust and strong? Absolutely. And I will demonstrate that in a second. So here's an example of Huygens element. I mean, you can use a variety of elements, but this is one thing that I'm using as an example. It's electrically small. There's a via here. It's a cross shaped with a ground plane backing. And this is how the schematic looks. See, this is the antenna. The antenna is an ensemble of 1, 2, 3, 4, 5, 6, 7, 8 by 8 elements backed by a ground plane. This is the feed. What you see on the right hand side is a corporate feed backing where we connect a 50 ohm feed source. And this is how it looks if we build it. This is looks from the side. And my comment is that antennas can be even very beautiful. They don't have to be ugly, and as we've seen in the old days. All right, this is the feed network, and this is the question: will it work? Yes, absolutely. We can have an 8x8, the 8x8 element antenna that I showed you can have a very, very effective radiation in the broadside direction. Okay, 11.7 gain. The gain is 11.7 dBi. That's very, very impressive, actually. And this is a plot of the gain versus the angle. So it can be highly directed. Okay. The nice thing about this concept is that we can incrementally increase the gain. We couldn't do this before. So here I'm adding one on each side. So I have 10 by 10 elements, an antenna of 10 by 10 elements, and I have a gain of 14.7 dBi. The beauty of this concept is that I can use it for conformal or conformable surfaces. And no theory had been developed in the past that addresses conformable surfaces. And this is extremely important for a variety of applications. So what happens, how we do it is that we take a plane and we say that we want the radiation to be normal to that plane. So you choose a direction of maximum radiation, and then I find the plane that is normal to that direction, and then I phase each element such that I have a phase front along the plane that is normal to the direction of maximum radiation. Okay, this is just another example. Now, will it work? Here's a demonstration to show you whether it works or not. This is a half circle, half a cylinder antenna, which is shaped like a half a cylinder, and we phase each of these elements. And the outcome is that it gave us a very, very nice radiation in the direction that we wish, which is extremely encouraging. And of course, one can use it for a variety of applications when you need a conformable surface, like a drone. And I don't imply that all drones are for military purposes. We can have drones that deliver chicken, like in this one here, Kentucky Fried Chicken. So, but the point is that drones are suffering from many problems. They call it blackout problems. And this may serve as a solution for the drone problem. This is more exotic examples, and we show you here that even for this challenging surface, I can have a gain of 19 dBi. Quickly, in the last 3 minutes that I have, I'm going to show you that we can extend this concept of building blocks to building lenses. So the question is, can we design lenses by careful stitching of building blocks? With all fairness, the one who really came up with this concept of building lenses using electrically small things was Federico Capasso, who is presently at Harvard. So we didn't, so he used metallic elements to create a lens which is flat, which you see on the right-hand side, that can focus a green beam. Okay. Of course, there are many challenges with what they've done, but what we did is that we said, can we create something similar, but at a much lower frequency, but using the dielectric elements with careful stitching. And this is, let's hope it works, this animation. This shows that indeed I can direct the energy using, of course, the mathematical model of the wave into the direction that I wish. Of course, there's a limit to this. The limit is the contrast variation in the dielectric, but the concept is workable. I can do flat lenses here, flat lens focusing. Look at this. This is a demonstration. You have a plane wave coming from the far right. This is a flat lens, and it focuses the energy without the need for the convex or concave lenses. And here's a flat reflector. This is a fully flat reflector. The wave is coming from the far left. look what happened to the reflected wave. It's going in a direction of 30 degrees of normal. So many interesting things we can do. Also cloaking. This is on the top picture, you see a PEC object, which is perfectly electric conducting, and you have a plane wave coming, and you see a lot of reflection. And the bottom one, you have a plane wave coming, and if you're standing here next to the plane wave, you cannot tell if there's a PEC object on the far right or not. See? Which implies that I have cloaked the device. That's what cloaking means, that the observer who's standing right here cannot see any energy coming back. All right, and so in the last 30 seconds, I conclude with some thoughts. Okay, we need to rethink how EM devices evolved. That's not being an anarchist. For the students that don't think that this is a statement for anarchy. No, this is a statement to make us do a better job. Okay. Good evolution is a systematic process that starts from a fundamental building element rather than a designed element that, was inspired by a dream or someone. The end result, of course, is a good design. Our increased sophistication in the EM field requires high sophistication in analysis and equally higher sophistication in synthesis. The two go hand in hand. We cannot synthesize more impactful devices, more needed devices that address key challenges without going back into analysis. And I would say that the electromagnetic field future had never been so exciting if we only focus on the physics rather than the math. When I say we focus on the physics, that does not mean we ignore the math. The math is the language. I'm talking to you using language. Okay, so one more time, we need to give more attention to the physics rather than the math for those who are in the field of electromagnetics. And I will conclude with this slide. I say you need to rethink the EM field. Just keep this in mind, model-based electromagnetic systems as opposed to physics-based electromagnetic systems, okay? That's something for you to ponder upon. And of course, there's no work that is fully completed. This work is continuing, and hopefully we will share more interesting things with you in the future, just like look at this exotic Lego, what these people did with this, with Lego, this beautiful creation. I will stop right here. I think I went overboard by 2 minutes. Forgive me, Zbig, and I will be happy to entertain any questions that you may have.
Well, thank you very much, Omar. I was mesmerized by your talk, and I hope everybody else was. Okay, I have lots of questions. Many philosophical, I must say, but after my period of fascinations with quantum, quantum physics and Schrödinger equation, I humbly admit that Maxwell equations are much more challenging, and at the same time with, I guess, more tangible consequences in the world. So anyhow, I will now invite the audience for questions. Andrea, do we have any Q&A things there, or
not yet, Spig?
Not yet. Okay, so Omar, I have where to start, right? One thing which really, I don't know. I mean, you showed this stick antenna, right? And then you said, we still don't understand how it works. And I said, Jess, no way. We have all this, we can build it from these little blocks now, right? And, is that true that those stick antennas are just, you put them together and say, okay, now I remember still when I was a kid and my grandpa was saying, no, just shift this antenna a little bit because we're losing the signal, right? So is this how those things work? Or there's more?
Very interesting. You asked that basic important question. I remember when I took my first antenna course in Illinois way back when, I asked the late Professor Paul Mays, who was a genius, was a pioneer in antennas, and he was actually one of those who developed the log periodic antenna. I simply dared to ask him a question at the end. I said, Professor Mays, why the dipole antenna radiates? And he looked at me. I remember this was in 2005. No, I'm joking. One digit before. No, this was in 1985. And I asked him, Professor Mays, why does the antenna radiate? And he looked at me and I remember he said, the current comes and then the energy goes. I wasn't happy with that. And of course, this is not to belittle Professor Mays. He's a giant in his area. But my point is that there was no focus on the physics of radiation. There was a focus on how to solve the problem, because we've gone through a period where people want to just design. Don't waste my time. Design, make it work. Let's move on. And I'm not belittling that. Many corporations, they want, time is important. They want to design and move on. But if we want to go beyond that, and here's an example of conformable antennas. There's no theory at all that addresses the problem of conformable antenna. So when we go back to the dipole antenna, actually, there are many things that we don't know yet about the dipole antenna. Professor R.W.P. King, the father of the dipole antenna, and he wrote the book. I think he spent 80 years of his illustrious 100-year life just researching the dipole antenna. I did a lot of work on the impedance of the dipole antenna. And especially when you load it, you have all kind of things. So it's not a trivial question. It is absolutely not a trivial question. That's number one. Number two, when we conflate the mathematical concepts, i.e., there are 6 field components to the electric and magnetic fields surrounding the antenna, that makes the picture extremely exotic and complex. However, if we look at the power, and very few people look at the power, okay? If we look at the power, then interesting things start emerging. Very interesting things start emerging, okay? So the question you posed is really interesting. It applies to the microstrip patch antenna. I'll tell you a little anecdote. A luminary professor came to serve on one of the PhD students in our department, one of the most, if not the most decorated in electromagnetics. And I remember I asked the PhD student, can you please explain to us how the microstrip patch antenna radiates? And this was a PhD defense. I remember him so vividly looking at me, and he said, Omar, let's go there. I remember so well. He said, let's not go there. Okay. So, now when we hammer at these questions, I think we really start going back and to say, why should I use this? Right? Why should I? In other words, this is my point. Why should I waste my life trying to understand something that was not based on foundations, on building blocks? That's my point. Now, please, what I'm saying here is subjective, okay?
But thank you. Yet I must humbly admit that it only recently, and to some degree, thanks to the defense, the PhD defense of one of your students, I was invited to. I started to appreciate the grand challenges which are facing the electrical engineers, particularly those dealing with radiation, right? And this is that going down to the little components is really the way to start to understand what's happening, right? And the shock of this dipole, simple stick antenna, and the fact that it's just too complicated to tackle at this point, probably still in an accurate way. It's a revelation for me. Now, before I keep going on that, let me see if there is. Do we have anybody else knocking at the door, Andrea?
I actually don't have anybody just yet.
Okay. Well, I think everybody is just listening to what is unfolding to be an interview with the electromagnetic master here. The part which I was taking a little bit as for granted is that now we have all the supercomputers. Mind you, again, building blocks in them, in billions, right? So we have all those supercomputers which we throw, all those mathematical kind of questions. I mean, physical questions formulated in math there, and they spit out this beautiful three-dimensional graphs, and some of that you did show, and yet they are not quite there. Where it comes to accurately modeling, the objects which are not just atoms, right? Not just two atoms, not an array of atoms which are crystals and stuff like that, but a real, metamorphic surfaces even, those are man-made. So the question is, what power do we need to actually be able to play, rather than going for the expense of nanofabrication or microfabrication and putting those things together, really play real time kind of on the computer, say, okay, I shift this one, I just bend it a little bit, well, let's see where the beam comes out, right?
Yes, I fully, I sympathize with that. I'm advocating the following perspective, is that I'm not diminishing the importance of modeling. I'm not diminishing the importance of mathematics. I mean, this is the tools. These are tools. But what I am saying is that I'm saying that in the field of electromagnetics in particular, I think that the golden age of electromagnetics evaporated or disappeared when all the attention shifted to solving a problem, not understanding. Now, I understand that we cannot have our graduates go and work in a company just to explain to them how it works. I mean, no company, because we're engineering, it's an engineering department, granted. But if we want to meet key challenges, we have to go back and understand how things work. And a key example is in the area of biomedical engineering. Here's an example. 30 plus years and people have been trying to use microwaves for breast cancer detection. Nothing came out of it. Nothing. Okay. I think, hopefully in the future, I can give a talk on this. I think I do know why. Because our perception has been frozen. We froze our thinking with something that was done long time ago, and we're stuck with that paradigm. We're stuck. I mean, this might sound like blasphemy. We're frozen with the electrical field and magnetic field having 6 components paradigm. We're frozen with that. Okay, so when I had a debate, very interesting conversation with a graduate student just 2 days ago, and I emphasized to him that the model is part of reality. It's not all reality. And this is my point. When we think that the model represents all reality, we have a dilemma. Okay, I cannot talk about your field and quantum and others and nanofabrication. I'm sure there are parallels between them, you know, in terms of the perspective that we have towards these fields. But what I'm saying is that we really need to go back to physics. And in the field of electromagnetics, not to be physicists, you know, there's a physics department out there, but we need to make sure, and as far as the field of electromagnetics is that the physics is a core part of the field. Okay, you know, nowadays we have simulation tools that are so powerful. And I want to say a word to the graduate students. I mean, they came to the school here knowing that there are simulation tools, but they have no idea what it took to develop these simulation tools. Okay, so now we have simulation tools that are virtual laboratories, right? So with these virtual laboratories, we can go into two directions, possibly more, but to simplify, we can have graduate students that become just good designers, end of it. Or we can have graduate students that will discover new things with these tools. Okay, now this is not the right time and not the right space and time to talk about it, but I can give you a solid demonstrations of that. Very, very solid demonstrations. In other words, in summary, there's so many interesting things to be discovered yet. There's so many interesting things to be discovered yet. And I'm not saying this to, you know, to attract people into this field, but this is the reality. There's so much. And just very briefly, that the log periodic antenna was discovered. I would say it was, sorry, not the log periodic, the Yagi-Uda was invented, discovered, call it whatever you want, I think in the 20s or 30s. Don't you think that we can do better?
Yeah.
Right?
About it, you know, I wish, well, no, it's not just a wishful thinking, you know, we are going to sit down and really have a good chat. I must say that of all the seminars I attended, I don't know for how long, yours was inspiring, you know, no kidding. I'm shifting my attention to electromagnetics. Okay.
Thank you.
So, Andrea, I don't think we have many students left at this point. We already.
Well, actually, they're all here. They're just
here.
I can see the participant list. They are here, but it's a quiet group today.
They're quiet. No, I think everybody is just wow. Okay, I really appreciate you taking it in this, you know, in this Lego way, okay? And for me, and you know, well, let's face it, you know, I have been around in physics and you know, studying some of the electromagnetics, and I did find it very refreshing and exciting.
You know, I want to show you. I want to show you a very quick slide that I hope the students will look at it and reflect on it. This one here, you see, this is something that is quite, you know, in my opinion, extraordinary in the sense that we designed a surface here at the bottom that absorbs all the power that falls on it. And it is not based on the concept, the classical concept that Professor Senior, the late Professor Senior at the University of Michigan came up with, I think in the 70s, the so-called surface impedance. In other words, I can absorb all the power without having a 377 impedance, i.e. free space impedance. So now, if I didn't show you this and I were to ask you, design a surface that will absorb all the power coming from free space. And let me simplify it, that it's a flat surface, Okay, you will say immediately, based on the books that we have, that it has to have an impedance of 377. Here is a demonstration that I can do it completely using different concept. Completely. Okay, and these are the things that I'm talking about. Now, is this a philosophical statement? No. You know what this is for? This is for energy absorption, electromagnetic energy absorption, which means that I can have absorption that is near unity. You know, to me, it's not intuitive at all. I mean, you have a plane wave coming and hitting this structure right here, and all the energy being absorbed. Absolutely, it's not intuitive. Okay, so these are the possibilities that we can do. These are the possibilities. So this is, so if people, you know, were patient with me at the beginning, we're not talking about religion or philosophy, but we really have to, at least for our graduate students, to rethink why we do things in a certain way. You know, why we, this is very, very important. And I told you that it's a true anecdote when I told you that I asked Professor Mays, I remember 1985, why does it radiate? You know, why? Okay, and if we can do, if we definitely can do much better. Now, I'm not interested personally in military applications. These are important, but I'm interested mostly in biomedical applications. And there in that space, I think the field is wide open for so many interesting things using electromagnetics. And the last thing, if I may say, people think that it's always exciting to go to higher frequencies. I don't believe so. I think that the challenges and the more exciting and the fun stuff in lower frequencies. The higher the frequency, the simpler the analysis. The lower the frequency, the more complex the physics.
Yeah, that is, you know, I would say not necessarily intuitive. There's the little, you know, like, you know, intuition after all is built on our experiences, right? And that's exactly where searching for physics behind that is going to help. So, well, Omar, thank you so much. All right, I think it was a great seminar and very, very well. You know, it's one-on-one discussion, but with hopefully audience is listening and excited about all that. I think we have to stop here, and I will be chasing you on the campus. I really want to talk about that.
Look forward to it.
Okay, take care.
Take care.
Thank you.
All the
thank
best.
you everybody for attention, and thank you, Andrea, for hosting this seminar for us. And well, I think next month we will have another seminar. Okay, but that's a good example here. All right, take care.
Have a good day, everyone. Bye.
Yeah, bye.